Talk about is my some research that I did that I think is going to be very intellectually stimulating. We shall see. So the presentation is what I'm going to give is psychosomatic effects at low doses. This is my lab here. This is where I do electron paramagnetic resonance, my lab for thermoluminescence and optically stimulated luminescence. Got a lot of other fun toys there. I would actually claim I have the coolest lab on campus. Very cool research that we do. But this is something that I did because it wasn't funded, and so I had to do it on my own, so I couldn't have a graduate student do it. So we're going to talk about the theories of what happens at low doses of radiation. What are the current scientific theories that are out there? Let's talk about those. So the first one is going to be hormesis. So what we see here are just some theoretical models for the health effects of radiation at low doses. And this is all simulated data. None of this is real data. I'll show you real data later. But what we have here are different models of possible interactions down here. Now what I'm showing you here is places where there's really just noise. All of these are basically fitting a function to noise. And fitting a function to noise is meaningless unless you're trying to come up with regulatory basis for protection against doses down here where all you have is noise. Now, the first model I'm going to explain is what's going to be called hormesis. Now, hormesis is effectively saying that a little bit of radiation is good for you. And you might think, why would a bunch of scientists think that a little bit of radiation is good for you? Well, there's actually a lot of published literature claiming that a little bit of radiation is good for you. And so let's talk about that. What is the science out there that makes that claim? Well, one of them is strictly the idea that evolution optimizes organisms to their environment. And currently, biologists tell us that life started, something like 3 billion years ago. And as I think everybody knows, radioactivity decays exponentially forward in time. If you go backwards in time, it exponentially increases. So that if life was designed for the environment of the Earth 3 billion years ago, the radioactivity that was here would have been exponentially higher than it is today. It would have been substantially higher. And so those original cells, whatever they were, prokarya, archaea, whatever they were, they would have been designed for higher radiation fields. And so the mechanisms, the proteins, the DNA, the RNA, all of that mechanism that was in place for the first cell, it would have optimized for this higher radiation environment. And so the argument there is that, well, that's carried on to today. That was the original design for life. Whatever those cells were that were able to proliferate and continue on till today, whatever was in that design specification is with us today, and that's a higher radiation field. So there's a lot of literature that says that. Now there's other literature that says, well, we're not single-celled organisms. We're very different. And so they would contradict that. Now there's other research that would say something that is far more compelling. Now, normally when we define something to be carcinogenic, we take a bunch of rats or mice or something like that, and we feed them a bunch of this stuff, or we expose them to a bunch of this stuff. And when we do that, if they get cancer as a result of being exposed to a bunch of this stuff, then we say, that thing is carcinogenic. That's typically how we do it, unless it's radiation. When it comes to radiation, we do the opposite. Those who are in the nuclear industry know that things are generally quite opposite. They're not really the American way in the nuclear industry. In the nuclear industry, we take the approach that we assume that an operator has failed. We assume that the operator is guilty, and the operator then has to prove that they're innocent. The operator has to document everything. If it's not written, it did not occur. Literally. It's kind of un-American to say, you are guilty unless you can prove that you're innocent. And that's how we do it in the nuclear industry. A regulator comes to the site and says, I believe that you did not follow your procedures. Prove to me you followed your procedures, and you're going to have to spit out all of the attachments that were filled out correctly and all of the surveillances and so forth, and then I'll believe that you did what you were supposed to do. In a like manner, as we do pretty much in anything else in nuclear, we do that also when it comes to carcinogeneity, radiation-induced cancer. And the reason why is because when you do low doses of radiation to rats, it's actually radioprotective. There's a bevy of papers that have shown that if you give a rat radiation, it's become radioprotective. It's less likely to get cancer up to some level. These are actually rather high. And you can even help to protect against acute radiation syndrome if you give it a predose. And so there is some compelling evidence out here. Now that doesn't convince everybody. Basically, what would probably convince everybody is if you did that with primates. If you gave primates those kinds of doses and primates showed radioprotection, then that would I think that would be the last nail in the coffin. And so what we do in health physics, the nuclear industry, is we're going to assume this linear line, which is clearly much more detrimental than this hormesis effect down here. Now, what I'm going to show at the end of this presentation, after I explain all of these others, is this one right here, this superlinear effect. This is what my paper showed, is that we have actually a superlinear effect. You might think, well, that sounds pretty crazy. That sounds pretty crazy. But I'll prove it. I'll show you how I'll show you how I proved it to the editor and the reviewers of the Health Physics Journal. Okay, so that's hormesis, the idea that a little bit of radiation is like medicine. A little bit of medicine is good for you, too much medicine is bad, right? You get a healthy dose, whatever your provider prescribed, you're good. You should toot that, but you don't double it. That's bad. You don't want to take double the dose. You want to take the optimal dose. Okay. So the sublinear model. The sublinear model, if you go to the literature, the sublinear model says, yeah, okay, the original life that precluded everything that we see today, that had a design spec for the Earth 3 billion years ago. But Homo sapiens, we came about, millions of years ago. Millions of years ago is a lot different in terms of the radiation field than what you had billions of years ago. And so, okay, if our design specification is for the Earth and the biosphere millions of years ago, yeah, the radiation levels would have been higher, but not by a lot, not by a whole lot. So the design specification is that a little bit of radiation isn't going to make a lot of difference because that's basically going back to the radiation levels where Homo sapiens first emerged. When we first emerged, that would be more like our design specification. And so then after that, then you get an effect. That's kind of the sublinear. Now the sublinear is very much like the linear with threshold model. The linear with threshold model, you can see these two look kind of similar, right? It's not a whole lot right here, and then they start to increase. The linear with threshold model, if you go to the literature and you see why some scientists prefer that, is that the analogy to understand the mechanism is simply the body's ability to withstand a threshold level of insult. So if you take the design specification that life has for the biosphere, there's a certain amount of pressure. There's a certain range of pressures, a certain range of temperatures, a certain range of oxygen, a certain range of impurity in water, a certain range of vibration, right? So I mean, it's healthy to jump off of a 10 centimeter block 100 times, right? That's how we're designed. But we're not designed for a single jump off of a 10 meter block. It's the same overall, right? But it comes down to the frequency and the magnitude, right? It's healthy to take a jog around the block, right, with the impact that gives onto your feet. But if you took a baseball bat, right, there's a big difference for what you're designed to be able to overcome. One is going to make you healthy, not have any effects, and one is going to overcome your body's ability to repair itself. And you're going to have effects. And so that's the same theory that you basically have with the linear with threshold, is that the body's able to repair itself. Because radiation's ubiquitous, it's always been here, it always will, and so you expect that life has come up with mitigation capabilities for that. Just like every other kind of an insult that we have, bacteria, virus, funguses, life has evolved to have some ability to mitigate that so that it can thrive and not just simply take a dive whenever one of those insults occur. And so that's basically this idea right here, linear with threshold. That's if you go to literature, those are generally the technical bases by which you'll see these. Now the linear with threshold. Now this is what we've historically used for basically our entire history in the nuclear industry, is that we use this model. So we ignore the potential for any of these kinds of things, that radiation might be rather harmless at low doses or have absolutely no effect up to some threshold dose, or that possibly a little bit of radiation is good for you, like medicine, like what happens with rats, that maybe we're like rats. I don't know if anybody wants to think you're like a rat, but that's usually what we do, except for in nuclear, right? We'll default to the conservative. You assume it's as bad as it could possibly be, and then you have to make that okay in your design, right? Double guillotine break in your primary coolant loop, right? Act of God happens, just assume it happened. Don't need a reason why. You just assume the worst it could possibly be does occur, and then nobody can get hurt, right? That's how we do business, right? And so that's the same kind of a concept you have here with LNT. It's simple, making it, in that sense, elegant, and we know it's conservative. Now, there is a technical basis for it. There's the Health Physics Society did a survey recently talking about the executive orders, which told us to give up this and to go to something that you have more defensible. Before I tell you the technical basis for LNT, I will say I was surprised to find out that less than 5% of the health physicists on that conference call felt that there was adequate technical basis for LNT to call it scientific. Now, it is scientific in the sense that when I get way up here, I can see that the data will become linear when I'm not in the noise. Because right in here, it's just all static for all intents and purposes. This is, you just get a bunch of data points that are just scattered all over the place, and you're trying to fit these lines to a bunch of noise. But the technical basis that those who have published in the literature that defend LNT, there's not a lot of them, but when they do, it comes down to this. The current scientific model for radiogenic cancer is double-strand breaks of DNA. Now, we can't tell you where in the DNA, nor how that occurs, but we do know that there are a lot of other things that can cause cancer, but when it comes to radiation, there's this large chunk of what we call, we used to call it junk DNA, now we call it dark DNA, because as we started learning more and more about cell biology, we realized that this DNA actually had function. It's kind of hard to tease out what that function is. And so it's easy to just say, well, there's somewhere in the dark DNA for certain kinds of cells, if you get a double strand break, because we don't know what happens, right? It's basically the code for all of the infrastructure, this huge machine of the cell, that it's easy to say, well, that could do it. And it could, because you can't say that it can't. And since you can't say that it can't, you can say that it could, and if it could, it's the easiest explanation. And so we default to Occam's razor, because we don't actually have a better explanation. We don't. And so you don't have a better explanation, and this would explain it. Somewhere in the dark DNA, you get a double strand break, or something like that, and it starts to cause the proteins to do something different. So you can't you can't receive a signal to die from cell death, or you don't have a throttle on the cell's trigger to reproduce. And so, as such, it is currently the best model for LNT, is that you have double strand breaks, and you know that double strand breaks are going to be proportional to dose. If I double dose, I double the probability of a double strand break, and that would explain way up here why it's linear. Why it's linear with dose. The probability of cancer becomes linear with dose. And so now I'm going to argue what we actually see in humans is going to be this superlinear. You might think, that's just crazy, right? Why, after all this scientific evidence, would you find in the literature that there's a superlinear effect? This is going to be interesting. So this is where I published it. And let me tell you why there's a very good, strong, scientific, technical basis for the superlinear effect in humans. And I'll preface it, and I'll probably reveal the reason when I tell you, you only see this if the people knew about the exposure beforehand and were terrified by it. Then this occurs. When they didn't know about the exposure or weren't terrified from it, you're going to see this down here. So let me give you some examples as to why that is such a tangible and potent explanation of what's observed. So there's all of the references are in the paper. So there was a group that found this amazing epidemiological study. So during Chernobyl, the country of Estonia was part of the Soviet Union. And so the men from Estonia that were in the army responded to Chernobyl. Now, not all the men of Estonia were in the army at the time. A lot of men weren't. So after Chernobyl, these researchers said, wow, look, Estonia got little to no fallout from Chernobyl. It was basically clean, it just kind of skirted around it. And so it made for this amazing epidemiological study. So that you could basically say, we have men that have the same genetic distribution, they have the same lifestyle, they eat the same food, they do the same activities, they live in the same neighborhoods, they dated the same girls. One group of them responded to Chernobyl, the other didn't. So let's see how the disease rates compare. It's like the ideal epidemiological study. And when they checked it in the early 2000s, they didn't see anything. But by the time they looked again in 2024, they did see a small, statistically significant increase in cancer rates for these men. That's not a surprise, right? They were liquidators. They responded to Chernobyl. What they did find, what was staggering, which was heartbreaking, was that the men that responded to Chernobyl had a 600% increase in suicide rates. Overwhelmingly, that was the main health effect. It was a psychosomatic effect. And they figured out why. Basically, if you had responded to Chernobyl, you were, one, stigmatized, right? Ooh, am I gonna catch it? Right? What have you got? You got some Chernobyl contamination, right? There was a stigma that came with that. Then on top of that, they didn't know, right? They might have been told, oh, you got a low dose, right? You get a low dose from Chernobyl, what does that mean? How do you interpret that, right? These are soldiers, right? These are soldiers. How does a soldier interpret that? Not a nuclear engineer, not a health physicist, a soldier. And so what they tended to do was whenever they had any kind of a normal medical outcome, they might get arthritis, they might start to lose their memory, they might start to lose their hearing, they might needing glasses, right? How do you know, if you're a soldier, that Chernobyl didn't either cause that or exacerbate it? I mean, this is Chernobyl radioactivity, right? What does that do, right? And as soon as you start buying into that it either caused this medical effect or made it worse, then anytime something happens, it just compounds your lack of hope. It's proof you have no hope. And when you have proof that you have no hope, that explains why the suicide rates were just astronomical, 600%. And so what they showed was this unbelievable thing, and I'll talk about this again later in the follow-on presentation, this absolutely almost insane result that the biggest health effect, the most deaths, the biggest harm to society from Chernobyl was fear. That was insane. That was crazy that it was that pervasive, the fear of radiation. And so if you go back and look at the literature, there are examples, the Taiwan apartment building. So they had, in Taiwan, they had some radioactive sources that got recycled, and that radioactivity got mixed in with construction materials. And so they made these apartment buildings where the people got large doses over long periods of time, but it was protracted. And because it was protracted, there were no acute exposures. And the cancer rates actually were lower, kind of like the rats. But it was a small sample size. It was a small sample size. But they didn't know about it, so they weren't stressed, they weren't afraid. If you go to the natural high background areas, there's a place in Ramsar Rand where the public gets about 10 rem per year. That's twice the legal limit for a radiation worker in the United States, 10 rem per year. At that dose, again, their cancer rates were less than neighboring areas where the dose rates were higher. But it wasn't statistically significant. It's a small sample size. If you go to any of the literature where there are claims of health effects from low doses, whether that's the Hanford site, the Downwinders, you go to 3 Mile Island, all of those places where you will find literature that claims that there was increased disease rates, what you can show from the literature is that those were places where the people knew about it and there was public terror about it. People were terrified about the effects of being exposed to 3 Mile Island. And so there's this thing, if you go to literature, it's called the nocebo effect. So I'm sure everybody knows what the placebo effect is. The placebo effect is that if I give you a sugar pill, around 1 in 3 people, if I give you a sugar pill and I tell you that it's medicine, once I've given you that sugar pill, you believe it's medicine, your stress levels go down. If your stress levels go down, you start to feel better. If you start to feel better, then whatever is going on, you attribute that to the fact that you now have medicine instead of a sugar pill. And 1 in 3 people will actually report improvements to whatever it was. Pain usually is what it is, that their pain goes down. Which makes sense, right? If you're stressing about the pain, and now you're not stressing about it anymore, it's not going to be as egregious. Well, the opposite also works. If I give you a sugar pill, about 1 in 3 people, if I tell you this is poison, if I give you a sugar pill and you believe it's poison, your stress levels are likely to go up. And you're likely going to attribute that stress, the effects of that stress, to the poison. And you will report measurable increases in pain and discomfort, even though it's just a sugar pill. Now, it doesn't work with everybody, but it works with a lot of people. About a third of the people will actually get both the placebo effect and the nocebo effect. And the process is called the HPA axis, the hypothalamic pituitary adrenal gland axis. And it's basically just your fight or flight. If you've got your fight or flight triggered on a regular basis, just from fight or flight, the literature shows that your cancer rates go up. You have any population, it doesn't even have to be people. It's easy to show for other things. If you stress an organism and keep it under stress, the cancer rates go up just because it's stressed. And so it can either be stress, fear, or depression. If it's prolonged and if it's extreme, your cancer rates go up. And so what I was able to show in this paper is that whenever you see in the literature, for all of the claims in the literature where there were effects to humans at low doses, in every instance, it was where the public knew about it and was terrified by it. And when you find instances where the public had elevated exposure, but they either weren't terrified by it because it's home, always lived there, or they didn't know about it, there were no effects, or it was actually beneficial. So that is the psychosomatic effect of low doses. So that's the end of the research that I did in low dose radiation. Hopefully in the summer my panelists can come and they'll show you their research because they've also done research in it. And I didn't actually even want to present this. I was going to present some other stuff. I'll show you that later, the one I was going to do. But this is just addressing somehow what they were going to address, but not focusing on their research, focusing on my research. So now I'll go ahead and take questions. Go ahead and kill the video.